I welcome you all once again to this course on CFD. We are now on to module 4 of week 1. Last class we have seen some review on basic fluid mechanics, governing equations, importance of terms, non-dimensionalization and why you want to do non-dimensionalization. Today class we particularly see vorticity stream function formulation, classification of equation, examples for each classification, solution nature. After that we will move on to the remaining syllabus content for week 1. We will quickly review what we did towards the end of last class. We observed that while solving Navier-Stokes equation, we have 4 equations, 3 momentum equation and 1 continuity equation. There are 4 variables, primary velocity variables u, v, w and pressure. Though we have separately equations for velocity, there is no separate equation for pressure, and pressure acts like a source term in all the 3 equations. The another major difficulty is convective term. We noticed that in convective term velocity multiplying its own derivative, which behaves like a nonlinear term, and solution is obtained only through iteration. Now there is a question, is there a way to overcome? So alternatively we have to devise an equation in such a way there is no pressure term, as well as whether we can remove or rewrite nonlinearity in the convection term. So towards that we take first 2D unsteady incompressive flow situation, 2-dimensional Navier-Stokes equation. So we rewrite here the full equation. We also write continuity equation for 2D steady incompressible situation. So differentiate equation 1, that is the x momentum equation with respect to y, and differentiate the second momentum equation, that is equation for v with respect to x, and subtract one from the other. This is a algebraic step that we are going to follow. So that is written here as dou by dou y of the entire x momentum equation and dou by dou x of entire y momentum equation. Now this operator dou by dou y needs to be operated upon each term in this equation. Similarly for the other equation. So what we do, we will take first term, explain how to do, also for the second term, then the procedure is repeated for the remaining term. So we will take the first term, that is unsteady term. So dou by dou x of dou v by dou t, which is coming from the second momentum equation, dou by dou y of dou u by dou t, which is coming from the first momentum equation, subtract one from the other, and we know this partial derivative can be interchanged. So dou by dou t common is taken out, dou v by dou x minus dou u by dou y is inside of it. Now we also know the definition of vorticity omega, we learned in the first class. So which is dou v by dou x minus dou u by dou y. So if you substitute definition of vorticity in this expression, then we get first term of the vorticity transport equation, which is dou by dou t of omega. You can repeat this exercise for each term. So here I am showing you for the second term, which is dou v by dou x and dou by dou x of dou v by dou x, which is the second term in the y momentum equation. Similarly, dou u by dou x, which is the second term in the first momentum equation, and you take a dou by dou y of dou u by dou x, and velocity is outside. So, this if you do, then we get u into dou by dou x and dou v by dou x minus dou v by dou y. This is same way, the common term, and here it is exchange. So, the common term is taken out. Once again we recognize the term in the bracket as vorticity. So, u into dou by dou x of omega. So, we get second term, which is like a convection term of the vorticity transport equation. We repeat this exercise for each term and we get a complete equation as this. So, rho into dou omega by dou t plus u into dou omega by dou x plus v into dou omega by dou y on the left hand side. On the right hand side, mu into dou squared omega by dou x squared plus dou squared omega by dou y squared. Now, if I look at this term, each of this term, first term is unstudied term, which is a local acceleration similar to local acceleration term in momentum equation, and next two terms are convection term similar to convection term in momentum equation. Now, we do replace them, rewrite this equation taking the definition of total derivative. So, which is capital D by dt of omega, and on the right hand side mu into del squared omega. So, equation 5, that is this equation, is actually parabolic in nature. We are going to talk about solution or equation classification in few slides down the line. So, right now we just take that this is a parabolic equation, and equation 5 is called vorticity transport equation. So, last class we had seen up to this point, we just wanted to review, and then we move on to the next part, that is a stream function. We know the stream function definition relating to the velocity, dou psi by dou x equal to minus v and dou psi by dou y is equal to u. Here also we start doing some arithmetic and calculus operation. So, take the first term, differentiate with respect to x, take the second term, differentiate with respect to y, and add them up. Dou by dou x of dou psi by dou x plus dou by dou y of dou psi by dou y equal to dou by dou x of minus v plus dou by dou y of u. So, on the left hand side you get dou squared psi by dou x squared plus dou squared psi by dou y squared. On the right hand side you can rearrange a little bit. So, minus sign dou v by dou x minus dou v by dou y. Again we are able to observe the term in the bracket on the right hand side, which is dou v by dou x minus dou u by dou y, which is a vorticity. Hence, we use the definition of that vorticity to rewrite that equation as dou squared psi by dou x squared plus dou squared psi by dou y squared equal to minus omega. In other words, del squared psi equal to minus omega. We number this equation as 7, and as I said before, we are going to talk about classification of equation few slides down the line, and this equation 7 is elliptic in nature, and del squared psi, if it is del squared psi equal to 0, such a equation is called Laplace equation, whereas if it is del squared psi equal to some source term on the right hand side which is minus omega, this is called Poisson equation. Now, we rewrite this equation once again, that is writing equation 4, which is a vorticity transport equation, and writing equation 7, which is in terms of stream function relating to vorticity, del squared psi equal to minus omega. Now, what do? We substitute this relationship, that is relating omega with the psi into this equation. So, each of this term omega are now written in terms of psi, and we will see how it. We also replace velocity variable u and v in terms of psi. We get an equation like this, dou by dou t, and then omega is replaced with del squared psi. Similarly, u is replaced with dou psi by dou y, and so on. Now, the common term, common sign, minus sign is a common, which is removed, cancel from the entire equation. So, you get a finally you get equation like this. Now, if you look at this equation, first this is a fourth order equation, because you have a fourth order term here, and then in this equation only psi is a variable, there are no other variables. So, it is a complete transport equation only with the variable psi, and this is a scalar equation, because psi does not have a direction. Now, equation 7, that is del squared psi by del squared psi equal to minus omega, and equation 8, which is a transport equation written only with the psi. These two together are called vorticity stream function equation. So, if you solve with corresponding boundary condition, then you get psi from equation 8, which is related to equation 7 with omega, that is vorticity, and from stream function psi and vorticity omega one can recover the velocity field u and v. So, now the question is, we started the vorticity stream function equation with the note that there is no pressure term, but we are also interested to know the pressure in the flow field. So, if one solves using a vorticity stream function equation, then how to get a pressure is a question. So, we will set up a procedure to get pressure from vorticity stream function formulation also. Once again, we rewrite the momentum equation for the sake of immediate reference, which is given here. What is given here is a u momentum equation. Again rewrite v momentum equation, and then differentiate first momentum, that is x momentum equation with respect to x, differentiate the second equation, which is y momentum equation with respect to y, add them together. I am not showing you the full all the steps involved in the derivation. We get a term finally like this, which is del squared p on the left hand side and remaining terms on the right hand side. Now, one can also replace u and v in terms of psi. So, we get another equation del squared p equal to 2 rho into remaining term. So, you can observe that once you have solved the previous equation 8, which is a transport equation written with the psi as a single variable, then omega, which is the transport equation for vorticity, from these two variable after solution is obtained one can get pressure field. Another point to observe, as you can see on the left hand side del squared p, and then there is a source term on the right hand side. So, this equation is actually pressure Poisson equation. So, instead of solving momentum equation, 3 momentum equation and 1 continued equation, it is also possible to approach by solving vorticity transport equation and get pressure field, velocity field as well. So, we move on to the next topic, that is classification of PDE. We know, we have already seen also here in fluid dynamics as well as in heat transfer, most of the transport equations they are all PDE. In general, PDE can be classified based on order. We have already seen first order, second order, fourth order, based on linearity, similarly based on the solution nature. Particularly here we are going to talk about classification of PDE based on how the solution behaves like. That is necessary to know, because that will also decide what kind of initial boundary condition is required, what kind of final boundary condition is required before getting into the solution of the equations. And it gives the idea the way or the direction in which the disturbance or solution propagates. There is a general procedure. Consider a linear second order PDE with the two independent variable, which is usually given here, and it is possible to fit any linear second order PDE into this generic form: A dou squared phi by dou x squared, B dou squared phi by dou x and dou y, and so on. So, it is possible to fit or rewrite any governing equation into this generic form. Now, this A, B, C, R and so on, they are functions of independent variables or constant. Now, we are going to make a classification based on the discriminants, that is b squared minus 4ac. In other words, if b squared minus 4ac is less than 0, if that value happens to be less than 0, then equation is, or the solution associated to the equation is classified as elliptic PDE. Similarly, if b squared minus 4ac is equal to 0, then it is parabolic, and b squared minus 4ac is greater than 0, then it is hyperbolic. Now, we are going to see details of this. So, in elliptic PDE there is no real characteristics, there is no specific direction preference. So, for example, if you throw a stone into a pond or well, there is a ripple generated or a wave generated, and you can observe that ripple or wave propagates like a circular fashion in all the direction. So, there is no real direction for the solution. So, information travels equally well in all direction up to the boundary. In the case of hyperbolic PDE, disturbance propagates at finite speed in a limited region within the characteristics curves. There are two characteristic curves in hyperbolic PDE. Compressible flows falls under hyperbolic PDE, and parabolic PDE, here information travels in only one direction along one characteristic curve. Now, having defined the classification elliptic, parabolic and hyperbolic, one tends to ask a question, what about the Navier-Stokes equation itself? The complete Navier-Stokes equation, that is unsteady term, convection term, 3-dimensional along with the pressure term on the right hand side, does not fall under any one such category specifically. They are coupled nonlinear PDE, and as we have seen before with 4 variables. We will now specifically see what is elliptic PDE. So, one of the example that is given here is Laplace equation or Poisson equation, squared phi equal to 0. This is called Laplace equation. This equation is a generic form. It has for pressure or for temperature distribution, phi can be any variable. If on the right hand side, if it is not 0, but it is with a source term, which is here given here as g of x and y, then that particular equation is called Poisson equation. Now, if you follow the discriminant procedure taking the coefficient values, so b is 0, a is 1 and c is 1. So, if you rewrite b squared minus 4ac, then you get minus 4, which happens to be less than 0, then you can also confirm that this is a elliptic PDE. So, in elliptic PDE, as we have seen before, the solution is not having any particular direction. It moves in all direction equally without any bias up to the boundary point. This is also given in this figure. So, you need to specify boundary condition on all the 4 direction, and solution is restricted full domain. So, next is a parabolic PDE. Again I am giving you one example, the one dimensional heat conduction or diffusion equation, and it is given with for alpha positive real constant as dou T by dou T equal to alpha dou square T by dou x square. It is a one dimensional equation, and capital T, which is to represent temperature, and the small t is for time, and follow the procedure of discriminant evaluation. B equal to 0 and C is equal to 0 and A is equal to alpha for this equation fitting with the generic equation. So, B squared minus 4 AC equal to 0. So, we know for that value the equation is parabolic in nature. So, as you can see here, the time derivative component appears, and we have observed that in Navier-Stokes equation first term on the left hand side is a time derivative term. The solution advances outward from a known initial values, that means it only marches in one direction, and you need to specify initial value. So, such a problem is also called marching type problem, and sketch wise it is given here. So, this is a starting and you specify initial condition, and there is a boundary condition on for different time value, and solution marches in one direction. You do not come back and try to do boundary condition implementation at time is equal to 0. In today's class we have done a complete derivation on Vorticity transport equation, understood the advantage of Vorticity transport equation, how to obtain pressure field as well as velocity field once you solve the Vorticity transport equation. The next topic we took classification of partial differential equation pertaining to solution obtained in fluid dynamics as well as in heat transfer. We have understood what is elliptic PDE with an example. We also described what is parabolic PDE and how does the solution look like. So, we will take another interesting topic in the next class. Thank you.